We're now firmly in the age of exoplanetary atmospheres. This is where space and ground-based telescopes are able to actually observe the atmospheres of other planets orbiting other stars. And what we've learned about this is absolutely incredible. We've sensed all kinds of chemicals, carbon dioxide, methane, water vapor in the atmospheres of these exoplanets. And of course, the hope is eventually we will see biosignatures, signs of life in other worlds. And the telescope that's been doing most of the observations that we're familiar with is James Webb and a bit of Hubble. Now, there are other upcoming telescopes that will participate and continue in this exploration of exoplanets and their atmospheres. My guest today is Dr. Ben Hord. He's a postdoctoral fellow at NASA's Goddard Space Flight Center, and he is a member of the team for the upcoming Pandora spacecraft, which is going to be launched by NASA. This spacecraft is small in scale, but it has a very specific job to do, and that is to examine the atmospheres of 20 exoplanets for days at a time and try to build up a very complete knowledge of both the star as well as the exoplanet and its atmosphere. And from that, when you can then compare against the kinds of observations that are being made from James Webb and then other upcoming telescopes like Ariel, you get this really much better ground truth understanding of what these planets are like. So I talked to Ben about the Pandora mission. Enjoy the interview. Ben, what is the Pandora mission?
I'm really glad you asked. The Pandora mission is an upcoming NASA mission that will observe exoplanet atmospheres and their host stars. And so to understand maybe what it's trying to accomplish that's different from, say, the James Webb Space Telescope, we need to maybe backtrack a little bit and understand how we observe exoplanet atmospheres. So the best way that we currently have to observe an exoplanet atmosphere is through a method called transmission spectroscopy. And so that's where, as a planet passes in front of its host star, the light from the host star filters through the atmosphere of the planet, and all of the chemicals and compounds in the atmosphere of the planet reflect and absorb the light at different wavelengths to different amounts, and essentially leave a fingerprint on the light. And so then that light travels towards us, and we can observe that with our telescopes and determine, well, this much light was blocked at this wavelength and this much wasn't. And we can back out maybe what the chemical compounds are in these atmospheres. But there's a big problem, because that means we assume that we know pretty well what the light from the host star is that's coming into the atmosphere and then being filtered through the atmosphere by all the compounds and chemicals before reaching us. And in the days of the Hubble Space Telescope and ground-based observatories, it wasn't a huge problem. But now that we're in the era of high precision with the James Webb Space Telescope, this is an issue, because we're finding that we don't really know stars as well as we think we do. They have dark, cool spots and hot, bright spots, and that changes very subtly the spectrum that is then of light that is then coming into the atmosphere of the exoplanet that we capture. And when we look at these planets, we don't resolve them. It's not like a nice picture of Jupiter that we can take with our backyard telescope. We see essentially just a point of light. We get just the star. So we're getting the light not only that's filtered through the exoplanet's atmosphere, but also from other parts of the star. And this leads to problems, because sometimes these changes on the stellar surface can mask or mimic features such as water in the atmosphere, which is a huge compound that we want to determine if there's water on some of these exoplanets, especially the terrestrial ones. And so this is what Pandora is going to try to solve. It's going to launch. It'll be in low Earth orbit, and it will observe a bunch of these host stars and their transiting planets to try and understand the effect that these stars have on our observations to more precisely observe the atmospheres of these exoplanets.
And I know that sort of this issue, this stellar contamination of the data has become a larger and larger issue and a larger conversation in the exoplanetary community. I think every person about exoplanets that I've interviewed in the last 6 months has brought this up as a confounding factor for the observations that they're trying to make, especially with the TRAPPIST-1 system. And I think we're learning that, like, the TRAPPIST-1 has, like, in some cases, like 40% of its surface is sunspots. And so, like, trying to know what is your signal, what is your noise, what is the star misbehaving compared to making those atmospheric sensitivities. So I guess, how will you be able to tease this apart?
That's a great question. So the Pandora is uniquely capable in that it will not only be able to observe in both the visible and the near infrared simultaneously, but it will also be able to stare for a long time at some of these planets. So the simultaneous observations are very important. In the visible, we can track how the brightness of the star goes up and down over time, and that allows us to see maybe what's the coverage of the spots in the hot regions and the cold regions on the surface of the star, and determine what fraction is covered, and we can kind of model that. But it doesn't really account for, well, if I have a really cold spot that's really dark over here on the star and a really hot spot, maybe they'll cancel each other out in brightness. So brightness alone in the visible can't solve the problem entirely. And that's where we need this simultaneous near-infrared capability. So hot and cold things emit light differently. They have different spectrums, they're different temperatures. And so obtaining this infrared spectral information at the same time allows us to disentangle how much of this brightness change is due to hot spots, how much of this brightness change is due to cold spots, because they don't scale linearly exactly like brightness would. So that way we can kind of attack it from both angles. And by looking at we have to look at them both at the same time in both wavelengths in order to get a full picture. And then doing that in long stares is very important. So James Webb Space Telescope time is highly coveted. I think you would be hard-pressed to find someone who does not want James Webb time. So it really can't stare at these targets for a long time. And so Pandora will stare at each of its targets for 24 hours and get that kind of like in-the-moment context of what the star is doing while we capture the planet transit and the atmospheric spectrum of the planet while it's in transit. So getting that real-time context, that kind of long stare, the short-term variability, and then revisiting each of the targets multiple times over a year, we can build up both kind of like an understanding of what the short-term variability of the star is and how it evolves, as well as the long-term variability of the star. And do the spots change? Do they go away? Do they move around? Is a spot that's behind the planet as it transits no longer behind the planet? And it's this kind of understanding of the star that we really need to get. And this is the niche that Pandora will really fill that other space telescopes can't.
So let's talk about target selection. How many stars and their planets are you hoping to be able to observe with this telescope?
So Pandora will observe at least 20 host stars and their transiting planets. This is a mission requirement. We have a 1-year-long prime mission. And so to stare at each for about a day, 10 times across the mission, that's 20 days per target. That's about 200 days. And so that leaves us enough wiggle room in case something goes wrong or there's an anomaly or we missed a transit, something like that. So we expect to look at more, but we're going to look at least 20 exoplanets and their host stars in order to just understand what's going on there. And so we have a tentative target list right now. It's published on our website, pandorasat.com. Anyone is welcome to go look at it and observe it with their backyard telescope if you want. But what we tried to do is prioritize both things that we think we'll be able to observe an atmosphere on if it exists, specifically water in the atmosphere, while also accounting for how variable is the star. So we want to understand this kind of stellar contamination effect. And so it's not really great to study that on stars where we don't expect to see that. So we have kind of two main parts of it's going to have a good atmosphere to study, we're going to get a good signal, and it's around a somewhat active, not too active star, because then our data is kind of washed out by noise. So balancing the two is really important. So the team developed a unique metric that kind of weights both of these factors, as well as some other weights to make sure that we're sampling a good swath of parameter space, because we want to observe planets around that are from roughly Earth size all the way up to Jupiter or larger, to get a good understanding of different types of planets, different types of atmospheres. And we're focusing primarily on low mass stars, so M and K main sequence stars. I'm glad that you mentioned TRAPPIST, because TRAPPIST is around an M dwarf star. And so these are stars that oftentimes can be very active. They have a lot of spot coverage, but they're also the stars that give us the best opportunity to find potentially Earth-sized, maybe even Earth-like planets transiting in habitable zones, or even larger planets like hot Jupiters. M dwarfs don't have a lot of hot Jupiters, but bigger stars like K dwarfs do. And so we can really get the whole range of planetary atmospheres in this regime.
And so when you think about, as you said, that time on Webb is very precious. And so you're going to provide this ground truth on the stars and their, on the conditions on the stars themselves. And then you're going to have the really high resolution spectroscopic data from Webb, and then your data, which they can then compare and go, okay, and now I understand how the star works, and I can figure out what is really coming from the atmosphere and then compare with those observations. So do you see it as sort of a partnership between Pandora and then Webb, and then even upcoming missions like Ariel?
Absolutely. Pandora is from the outset meant to be a complementary mission. It's not supposed to replace Webb or replace Ariel or anything like that. It's supposed to provide that context that I was talking about. So we do actually use a flight spare detector for our near-infrared detector for Pandora from James Webb. It's a flight spare from James Webb. So that not only helps cut down on costs, but it makes the comparison of Pandora spectra and Webb spectra that much easier. And so our hope is by understanding these stars and maybe even doing simultaneous observations with James Webb, we might be able to help them make their data even more precise, which would be amazing because it's already more precise than anything we've ever gotten. And so we've tried to tune our target list as well a little bit to account for new James Webb discoveries or planets that James Webb may be observing or has been approved to observe, to really maximize the amount of science that we can obtain from this observatory. It's a small observatory, but it's mighty. And I'm glad you brought up Ariel, because Ariel is going to be doing something kind of similar to Pandora, but not exactly. So Ariel is a big ESA mission going to launch hopefully at the end of this decade. I know they've made great progress on the observatory itself, and it will do something similar. It will look at exoplanet atmospheres in a dedicated way, and its bandpass covers a similar Pandora bandpass, and so it's going to be an amazing mission for exoplanet science as well, but Pandora will also help with that context. It's again, Ariel is going to be limited, like James Webb, in the amount of time it can stare at some of these targets. And so, especially when it's going to try and observe hundreds or even over 1,000 targets, it really can't dwell too long at the very beginning of its mission on any one given target. So Pandora is going to be very focused, very useful, and it's going to be here soon. I'd rather have data now than 5 years from now. And I think that it's going to be really informative to help the whole fleet of NASA exoplanet missions, not even the ones that just do spectroscopy. I think even the ones that do photometry, it'll be useful for calibrating, this one, we know that this star has a lot of spots, and we know that this planet might be, experiencing this type of interaction with the star. So it expands more than just James Webb and Ariel, and I think that it's definitely very complementary.
I love this idea that it's got a component that was designed for James Webb. So can you talk about that? You mentioned, what did you call it? You call it a flight
spare.
A flight spare. Okay. So what is this flight spare instrument?
So it's a near infrared detector. So in all of our phones and cameras and stuff, we have CMOS detectors, which is just essentially a visible detector. And those are easy off-the-shelf things. We actually have a CMOS. That is our detector for the visible in Pandora. It's a CMOS just off-the-shelf thing. It's super cheap because everyone's got one in their pocket. But near infrared is a lot more difficult and expensive to manufacture because we don't have one in our pocket. And so oftentimes missions, especially large missions that have very precise sensitivity requirements, will manufacture more than one detector. And that's because the process is either complicated and not guaranteed to produce a flawless result with any given iteration, or it's just not as well tried and true, and so you need to do multiple attempts. But for whatever reason, pick your reason, the James Webb Space Telescope manufactured multiple near-infrared detectors for its NIRCam instrument. And so it only has one up there in space. It doesn't have a spare in case one breaks down like a flat tire. So the rest were just kind of sitting around in storage at NASA. And so both in order to cut costs and to provide the Pandora mission with higher quality detectors and potentially unlock better data, we were given access to these flight spare detectors. So they have already been tested and quality controlled. They just weren't the best detector of all the testing. That one went up into space with James Webb. So these are like second best, which is still pretty good considering the quality of data that James Webb is beaming down to us.
But I think that's really great because now you have an instrument that is essentially identical to the one that Webb is using. And so that allows you to remove a lot of variability between the two. You know, if you had a totally different detector that was designed with different specs in mind, then you'd have to normalize the two. But in this case, it's essentially the same instrument. And so you can relatively straightforward way of comparing the quality of the data that you're getting. So I think that's great and very efficient to recycle all of this sort of into a new spacecraft.
For sure. Yeah, I think, recycling and low budget is one of the watchwords of the Pandora mission. It's actually part of the inaugural class of a new category of mission at NASA called a Pioneers mission. And so it's defined by how much it costs. But it's essentially kind of like a smaller mission that can still pack a big punch in terms of science. And so Pandora is punching above its weight. We probably wouldn't be able to have this detector if it wasn't already manufactured for James Webb. While staying under the cost cap. So Pandora is a real trailblazer in terms of what science can we do with maybe what's left over and what's a smaller budget and still provide really meaningful science.
So I want to talk a bit more about these sort of variabilities in the stars that you're hoping to look at. I'm not sure when your team, and your principal investigator started to lay down the foundation for this mission, but as I mentioned earlier on, you've got this sort of rising understanding that the stellar variability is becoming more and more of an issue. So specifically, what do you think are some of the kinds of things that you're expecting to see the stars doing while you're looking at them both with and without planets?
Yeah, so I think I touched upon it a little bit already, but we do expect to see the brightness change over time. That's very expected. I think diving more into the stellar physics, though, I do think we'll be able to get a much deeper understanding of the timescales on which the surfaces of these stars change. We've seen some stars that have a star spot that persists for years. We have stars that have a star spot that appear and then disappear within, the single orbit or a single rotation of a star. And we really only have our sun as the best example of what a star and its spots and how they evolve and the timescales look like. And so it'll be a really great calibration mechanism for our understanding of what stars are like. And I think this will trickle down to not only bettering our understanding of how to observe these planets, but also better understanding the spot physics and by extension, the flare physics and the activity of the star. And this is a huge issue for things like habitability. We don't want a star that's too active, but we want it to be a little bit active. And so understanding the sweet spot will be very helpful and informed by this understanding of the spots and how these regions change and how these active regions move around. I think another thing that Pandora will help elucidate that we're only now seeing with James Webb is the time variability of the atmospheres of these planets themselves. So like the Earth, atmospheres of different planets can be variable on time scales of, to us it would be our year, but to them it's their year, however many days that might be, how long their orbit is. But we're seeing now with James Webb data, with different visits of the same planet, different models and different types of chemical features are expressing themselves. And it's a bit confounding because we expected to see kind of a steady state of like, there's this much oxygen and there's this much hydrogen and there's this much water. But in many cases, that's not what we're seeing. And so, again, James Webb can only visit a planet so many times, but Pandora will be able to observe planets over and over and over again across its year-long prime mission. And so we do have some planets in our tentative target list that have been shown to have this kind of time variability and dependence on which orbit you're actually observing. And so I'm also really excited to dig into that and understand maybe what's going on here. What are the physics of the atmosphere? Is it because of winds? Is it because of seasons? Is it because of just chemistry in the atmosphere changing? Who's to say? And so I think Pandora will also help unlock those secrets.
Yeah, there was a story that came out like just this week where astronomers found winds on an exoplanet going like 33,000 kilometers an hour, and they were able to measure the velocity of the winds coming towards us on one side of the planet and measure the velocity of the winds going away from us on the other side of the planet, and then measure those differences and understand how fast the winds are traveling, which is kind of incredible. But you mentioned M dwarfs, you talk about K dwarfs, but what's it going to take to see stars like the sun and potential exoplanets that are passing in front of those?
That's the question that everyone wants to answer. And I think, unfortunately, the answer is two-pronged. The first is time. So the Earth orbits every 1 year by definition. And a lot of times it takes more than one orbit to actually detect an exoplanet. So whether you're using radial velocity or transits or direct imaging, even, you need to track the motion of the planet for as long as you can to make it a robust statistical result and be sure that it's a planet, it's there, it's not just noise. And so a lot of our instruments just maybe haven't been looking at single stars for that long. The best that we had so far was Kepler. And Kepler, as we all know, is decommissioned now. And so TESS is trying to fill in the gaps, and radial velocity is also trying to fill in the gaps too. It's doing a really good job finding other Earths. But then we run into the second issue, which is sensitivity, that a lot of times these Earth-sized planets are pretty tough to detect. They're small, so in radial velocity, they don't make the star wobble very much. The signal's not that strong. And in transits, they don't block out a lot of light. Especially as you get to bigger stars than these M and K dwarfs, because if you have a bigger star, there's more light that you need to block out to get that signal, and it's just tougher. So I think it's difficult, but I think that we'll get there in the coming years and decades as technology progresses to make the sensitivity better, but also as we just keep staring at some of these stars. We could get very lucky and see a single transit or something like that tomorrow, and then wait a year and maybe see it again. But I do think it just takes kind of dedication and persistence, as well as some technological advancement.
And I know with the Habitable Worlds Observatory, the goal is to directly image Earth-sized worlds orbiting around sun-like stars, use a coronagraph, block the light from the star, be able to actually observe the atmosphere of this exoplanet. And that's different than relying on that transit method. You're trying to make those direct observations. But is there a sort of, like a halfway point in between where you can do like a much either longer duration mission or different wavelengths? Like I know detecting exoplanets is easier in infrared, that the difference of brightness of the planet between the stars is less of a factor. It's like 10 billion to 1 with visible light, but it's only like 10,000 to 1 in infrared. And maybe I'm getting my numbers a little off, but is there sort of a middle stage, do you think, between what you're doing and then what will eventually come with Habitable Worlds?
Yeah, that's a really interesting question. I think, there must be, and I think that, Habitable Worlds will take, a decade or two or more to come online, and so it would behoove us to maybe have a shorter term goal of bigger telescope, something like maybe not quite James Webb class, but perhaps another type of telescope that can look for these types of planets through whichever method. And I think that the Roman Space Telescope might be a little bit of a happy medium. It will have a coronagraph on board. And so a coronagraph, it'll block out the light of the star to do some direct imaging. And it's going to have, amazing sensitivity. Not quite the sensitivity that habitable worlds would, but it will have better sensitivity than we currently have capability for with direct imaging. And so I think that could be a good stepping stone in both, cutting our teeth on the methods and the tools that we need to actually do this. But the coronagraph on the Roman Space Telescope is classified as a technology demonstration. So I don't work on Roman, so take this with a grain of salt. But my understanding is that it has a limited kind of duration of what it's actually supposed to be observing. I think it might be maybe like 90 days in the first 18 months or something like that. So it's not going to be a huge factor in the mission, on paper, but it could be that middle stepping stone of, let's try this direct imaging in preparation for habitable worlds. And, we have this old technology, this imaging technology with Roman that we understand and we know how to use. And so let's stretch the limits and kind of see what this next step is between now and habitable worlds, because there is a lot of technology development that will need to happen for habitable worlds to fly. We saw that with James Webb, it was delayed a lot because there was a lot of technology development that needed to happen. And so I'm hoping that this will allow us to maybe, try it and serve as a proving ground for that kind of thing.
Now, my audience is very familiar with TRAPPIST-1 system. So what is another system that isn't TRAPPIST-1 that you are intrigued by that maybe people should keep an eye out and sort of watch as events unfold?
Yeah, I think a lot of people are interested in the TRAPPIST-1 system because of the potential habitability of some of the planets. And I think that's great. So for fans of potential habitability, there is another system called TOI 700. It was discovered by TESS. It's also an M-dwarf system. It's host to 4 planets, 2 of which are in the habitable zone, and they're, Earth-sized-ish, give or take some amount. And so that was a much more recent discovery than TRAPPIST. And I think that might be a system worth watching because it's not only interesting that it has potentially habitable zone planets that are Earth-sized, but it also has a gaseous planet kind of near the interior of the system. And so it's interesting from a habitability perspective, but also from maybe a formation or evolution perspective. So we know in our solar system, the gas giants were really important in shaping how our system evolved, and some theories hypothesized that maybe Jupiter acted as like a shield for comets or like flung comets to Earth to deliver water and things like that. And so having this giant planet in this system could be an interesting test bed for these theories. And if we see water in some atmosphere, we can say, well, maybe there's water in these Earth-sized planets. Or if there's, if there's some mechanism that it could have gotten there that shields these planets from debris, what have you. So I think it'll be a really interesting test bed that TRAPPIST-1 doesn't afford, because TRAPPIST-1 is all similarly sized planets, kind of like ducks in a row from the M-dwarf. So I would say stay tuned for TOI 700.
That's awesome. Yeah. I mean, we don't have anything like that in the solar system. We don't have a giant planet that is closer to the star than the Earth-sized worlds. It's within the habitable, it's a very peculiar, bizarre system compared to us. And yet it's those comparisons when we can really learn a lot. So Ben, what are you sort of looking forward to as this, the schedule? Like, what is the schedule for this mission? When should we expect to see it launch? You say a year. Is there any real timeline on this?
So our launch readiness date is September 1 of 2025. So this fall. And so we are on track. Our spacecraft bus was just delivered. So the bus is essentially the brains of the spacecraft, helps with orientation and communication with the ground. So that's been delivered. That's a huge, huge milestone. So we're on track for that launch readiness date. We are awaiting our actual launch vehicle. from NASA. So because we're a small mission, we don't get our own rocket. As cool as that would be, we kind of have to catch like a ride shared orbit, like an Uber or a Lyft up to orbit with some other spacecraft. So we're waiting on NASA for that. They should be telling us sometime soon, hopefully. They've already got the contract out and are talking with vendors. So we're hoping that our launch will be not too much after the launch readiness date of September 1. So maybe hopefully October sometime, November. But it's tough to say at this point in time. But regardless of when we launch, we will have, like I said, a full year of prime mission. There's about a few weeks of telescope commissioning at the beginning, and that's just making sure all the instruments work and that we know what the noise is like and we know how to point the thing. And so that'll be important, but then we dive just right into science. And so I mentioned before that the prime mission targets will take about 200 days, but that leaves 165 days left, give or take, for other science. And we're actively soliciting the community for ideas, for targets, for research proposals. We can't give you money, but we can give you data. We want this to be as useful to the community as possible. So it'll be a year of interspersed science, main priority mission science targets with maybe whatever else the community wants to use this observatory for.
Now, what orbit are you going to be on?
So we'll be in a low Earth orbit. And I think when people conceptualize that, they think of, planet and it orbits somewhere around the equator. But that's not entirely true. We're in a low Earth orbit, but instead of orbiting kind of around the equator, we're orbiting kind of around the poles, almost like the Pandora is going to be the hat for the Earth. And that allows us to keep our solar panels pointed at the sun at all times. To keep this spacecraft powered, we don't ever have a lapse or a significant lapse in power to the spacecraft. So we will be occulted by the Earth at some points when we're pointing at a target, but we're making great effort to find other targets to point at, above or below or to the side or whatever, while the spacecraft is behind the Earth. And then once it comes back, it can look at its main science target again. So that's the kind of funky orbit that it has to be in order for it to operate.
Now, is that orbit partly reliant on the destination of the main payload for the rocket that you're catching, or you're going to have a kick stage that'll get you to exactly the orbit that you want to be?
Yeah, that's a good question. So the rideshare that we're hoping to take will ideally also be with other spacecraft that will be going to similar orbits. We don't have too much fuel on board the actual Pandora observatory spacecraft. We have a little bit just to do, some orientation and station keeping type stuff. But we don't have anything more sophisticated than that. So we're kind of reliant a little bit on whatever the launch vehicle is to more or less bring us to where we're supposed to be.
But the altitude, I mean, you've got that year of the main data, but the altitude isn't going to bring you down within a year. I mean, you're going to have more years that the spacecraft is going to be there, and assuming that it is fully operational, then hopefully you'll have extensions to your mission. Definitely.
Yeah. So we have enough consumables on board for more than a year's worth of operations, and all of our components on the spacecraft are stationary. We don't have any moving parts really. So that's fewer points of failure. And they're all rated for well over a year, well over maybe even 5 years of operational life cycle with 95% confidence. So it's entirely possible that Pandora just does such a good job in its year-long prime mission that NASA headquarters is like, hey, we should keep this operating. This is actually a really great mission. And headquarters has instructed the team to start thinking about it. That's not, that doesn't mean anything. That's not a guarantee. It's not a, hey, we believe in you, you should do this. It's a, be thinking about it. And so the team, that's an active discussion within the team because we would love a Pandora extended mission. And that would most likely be more community driven with fewer science targets because NASA is very big on open science, public data. So that would, again, we don't have any concrete plans yet, but most likely it would be a very community driven mission at that point. And it wouldn't even have to do exoplanets. It can do galaxies or supernovae or whatever anyone wants with a combination visible and near infrared observatory.
Yeah. Yeah. I mean, you can't say it, but I can say it, which is, wink, wink. These missions get extended all the time. You look at Curiosity, you look at Spirit and Opportunity, they're supposed to be on Mars for 3 months, and
right.
Opportunity was like over a decade. And so as long as the spacecraft is continuing to function, as long as there's science to be done, mission extensions happen. So I like your chances. Ben, what are you obsessed with right now?
That's a good question. I think in terms of science, I'm obsessed with the demographics of exoplanets that we're going to get. I think that with the Roman Space Telescope and LSST and the 30-meter telescopes coming online, I think we're just going to be so awash in data that we're going to discover so many potential exoplanets and so many edge cases of exoplanets that we haven't even thought about. I think we get tastes every now and then of what could be out there. Like, oh, it's 2 exoplanets in the same orbit, but on different parts of the orbit. Or, hot Jupiters were a huge discovery, or disintegrating planets, and we just don't know that many of them. And I think that these upcoming missions that are meant to be big survey missions are really going to push the limits of that, and we're going to discover really cool configurations and scenarios of planets that are going to make us challenge what we know and also make us dream. I think that science is really about dreaming for what's out there. And I think that's what draws me to astronomy. And I think that's what draws many people to astronomy. And it's these kind of just discoveries that the universe gives us that we didn't expect, that it makes those dreams come true, and it makes even more dreams happen. So I'm excited for just the explosion of data that's going to come out in the near future. And it's all going to be public. So there's never a better time to get into astronomy.
Yeah, I mean, you think about like when data release 5 comes from the Gaia mission, and you get tens of thousands of exoplanets. All of the Nancy Grace Roman is expected to find potentially tens of thousands of exoplanets. All of these big surveys, tests, and all of that. And I know what you mean. Like, you get these 2 questions answered. One is like, what's normal,
mm-hmm.
and what is it sort of statistically looking like the universe is shaking? What is a normal planetary system roughly going to look like? And that's one really interesting question. How normal are we as a solar system, right? But then the other one, as you say, is the weird stuff, the stuff that like, how did that? No one ordered this.
Mm-hmm.
I know there are exoplanets that are on completely tilted orbits compared to the rest of the exoplanets in the system. Like, how did that happen? And so I think I look forward to these just really weird possible configurations that sort of sets your science fiction imagination loose as you sort of imagine what it would be like to live on a world that is orbiting circumpolar compared to the rest of the planets in the system. Like, really strange situations. So yeah, I know that's all going to be exciting. More planets, more better. Ben, thank you so much for taking the time to chat with me today. Good luck with the mission. I hope you get a fun ride to space.
Thank you so much. Thanks for having me. Fingers crossed. Go Pandora.
Yeah. All right. We'll talk to you later. Bye.
Bye.
I hope you enjoyed that interview with Ben Hord and are excited about the Pandora mission, which I bet you didn't even know about it. So I'm going to talk a bit more about this work on exoplanetary atmospheres, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Bear Lake Roofing, David Gilton, and David Matz, Dennis Alberti, Dustin Cable, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Rohrbach, Sean Sargent, Spiderswap.io, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So at this point, I think we have very thoroughly reported on the hunt for exoplanets and atmospheres. We've talked to people about the work that James Webb is doing, about the observations of the TRAPPIST-1 system, and now you're seeing some of the future spacecraft that are going to come and join this hunt. And it really is the next level. Like, we're at the point where we have this rough understanding of all of the kinds of exoplanets that we see out there. And now the new generation, the new work is to study their atmospheres. And of course, this is all leading to the dream of being able to detect biosignatures in the atmospheres of exoplanets, to sense the gases that life might be giving off that will tell you that there is life on a world or not. And this will lead into the future with the Habitable Worlds Observatory. So we've got a ton of interviews here on the channel where you can look at this from every perspective, and I hope you can learn a lot more and be ready for those future announcements. All right, we'll see you next time.